So we are going to today do our lesson on solving quadratic equations by finding square roots. So if we just think back to a square root for a second, a number is a square root of another number if that number squared equals the other number. So for example, if I wanted to say like 2 is a square root of 4, that only is true if 2 squared equals 4, or 2 times 2 equals 4. Same would be true for, let's say, 5 and 25. 5 squared is 25, so therefore 5 would be a square root of 25. Now, a positive number will have to have 2 square roots. So if you think of 3 squared, 3 times 3 equals 9. So we know that 9 is a square of 3, right? So 3 squared equals 9. But negative 3 squared also equals 9, because negative 3 times negative 3 also equals that positive 9. So 9, the square root of 9 equals positive 3, but the square root of 9 also equals negative 3. So every square root has to have 2 answers. So if you have a positive number like 9, there's going to be 2 square roots, positive 3 and negative 3. Now, a lot of times as we do equations and things, you'll see that this negative will pop up in front, or sometimes you'll even have like a positive negative sign like that. So when we're solving for those solutions, those x-intercepts or whatnot in a quadratic, we would account for all of the options. But when we're just simplifying, as we're going to do mostly the first half of this lesson, you don't need to worry about the you don't need to worry so much about the plus minus. We're just going to stick to the positives for the simplifying portion. Okay, so a couple properties of square roots. So there's the product property, which just says that any number that's in a radical, if you break it apart into 2 of its factors, they would each have their own radical. And that also goes in the reverse direction. So if you had the square root of A times the square root of B, whatever that product is, if you multiply those 2 numbers together, would just be in a radical sign. The quotient property is when you have a fraction or something being divided inside your radical. And in that case, you would just have to separate the numerator and the denominator into their own radicals, and then they could each be simplified individually. So a couple rules for simplifying square roots. So a square root expression is completely simplified if the following are true. First, the radicand has to have no perfect square factors other than 1. So you have to make sure that it can't be divided by any other perfect squares like 4, 9, 16, 25, so forth. If it does still have another perfect square factor, then it's not completely simplified, and you would have to continue on with that problem. Number 2, there is no radical in the denominator of a fraction. And in that case, you would have to rationalize the denominator. So for example, if you had something like 2 over radical 3, this would not be allowed because there is a radical in the denominator. If, however, you have a radical in the numerator and your denominator is an integer, this one is okay. So no radical in the denominator, numerator is fine. And finally, there are no fractions under the radical sign. So if you have anything like this, you would not be able to leave it. You would have to simplify it or do something with it. Okay, so getting started, before we start simplifying, the first thing that I really want to do is just kind of list out all of our perfect squares. So if you want to, you can do this just by looking them up on your calculator. You might already be familiar with what they are already. So if I say to myself, what's 2 times 2 or 2 squared, I would get 4. 3 squared or 3 times 3 is 9. 4 squared, 16. 5 squared, 25. 6 squared, 36. 7 squared, 49. 8 squared, 64. 9 squared, 81. 10 squared, 100. 11 squared, 121. 12 squared, 144. 169, 196, and 225 would be 13, 14, and 15 squared. And obviously you could continue on doing that, but for our purposes, I'm just going to leave it at that. Okay, so when we're doing these square roots, there's a couple ways we can do it. For example, if I'm taking a look at number 24, I can use that property that we just came up with, and I can say, okay, what two numbers multiply to get 24? But I need to find the largest perfect square factor. So if I'm looking at all these factors here, I had 4, 9, 16, 25, and so on. The only one that would go into 24 evenly would be the 4. So I would have to rewrite this as a product of two of its factors. And then because one of those was a perfect square, which was the 4, that could then be solved, and I could have a 2 there. So I call this often the jail method. And the reason why I call this the jail method is because there's a corny little way that I used to remember. So I say, okay, you write down your two factors. Now the trick to this one is you have to come up with your largest perfect square, and 4 is the only one. So in this case, it's not a big deal. But I always say, if you are perfect, you are allowed out of jail, but you must change. You can't, like, think about it in real life. If you're in jail, you did something wrong, right? You can't get let out of jail and then not change. We're going to be right back in jail again. So the 4 was a perfect square, so it gets to come out, but it has to change to that too. The 6 is not a perfect number, not a perfect square, so it stays in jail or the radicand, and then that would be our answer. Now that works for some people who are really good about coming up with their perfect squares, but for some people it's a little bit trickier and they might miss a perfect square or something like that. So the other option is the factor tree method. And the other reason why I like this method is because it also works when we get to cubic roots and to fourth roots and all of those other roots. So if I have the square root of 24, another option is you can just start breaking it down using the factor tree method. The nice thing about this method is you don't have to come up with a specific set of factors that include a perfect square. You can come up with any set of factors to get you started. So factors for 24 are 2 and 12, 3 times 8, 4 times 6. So any of those would work here. So let's say we try 3 and 8, for example. Well, you want to keep breaking down each of those factors until they're prime. And remember, a prime is a factor that can no longer be divided by anything other than itself and 1. But the 8, however, is not prime. It's still composite. So I can break that down into 2 times 4. And then the 4 can continue on into 2 times 2. So now once you're done completely factoring your number out all the way to the primes, you need to look for pairs. Talking about a square root, we're looking for pairs because it's a number squared from the beginning. So we have a pair of 2's here. And then these other two numbers are just singles. We have a single 3 and a single 2. So those are going to have to stay inside. So whatever you have as a pair, one of those comes out. So since I have a pair of 2's, a 2 would come out. And then the two numbers that do not have a pair, this extra 3 and 2, would get multiplied and be back inside. And that gives me an answer of 2 radical 6. Notice it's the same answer I got using the other method. Okay. And then just to kind of show you another, actually, I'll just go to the next one. Okay, so now the next problem, again, I could do it the two ways. So if I want to use my jail method, so to speak, I would have to figure out, well, what is the biggest perfect square that goes into 96? Well, 81's more than half, 64 is more than half, 49 is more than half, so none of those are going to go in. 36 times 2 is 72, and 36 times 3 is too big. 25 does not go in, but 16 goes in. And if you kept working your way down, you would see that 4 also is a perfect square that is a factor of 96. However, even though I have two factors of 96 that are perfect squares, you would have to keep, or you'd have to use the bigger one, which is 16, to use this method. Now 16 is a perfect square, so it gets to come out of jail if it changes to its square root, and then the 6 is not, so that would stay in, and that's how you do it. So it's a little less writing, but it's a lot more knowledge of perfect squares and stuff like that in your head. So again, if that is a little bit trickier or you're afraid you're going to miss something or make a mistake, we can just use the factor tree method. So now when I do 96, I could break it into 16 and 6 if I wanted to, but maybe that wasn't like the first factor you thought of. Maybe the first one you thought of was 2 and 48. So then you can use those two. And now 2 is a prime, but 48 can continue on. So I'm going to do 4 and, oops, 4 times 12. Now 4 can keep going into 2 and 2. 12 can go into 3 and 4, and then 2 and 2. So now I have all my primes. Okay, so let's see what pairs I have. I have a pair of 2s. Whoops. I have a pair of 2s. Oh my goodness. I have a pair of 2s here, a pair of 2s here, and then I have these 2 leftover primes, this 2 and the 3. So I'm going to take out a 2 for this pair, a 2 for this other pair, accidentally drew the line through, and then my leftover primes, this 2 and 3, get multiplied together and they go inside. So my final answer would be 4 times radical 6. Okay, so continuing on with 300, you could break this up into a whole bunch of different ways. You could do 3 and 100, you could do 30 and 10. I'm sure there's other options you could use as well. So I'm just going to do 3 and 100. And then 100, you can go with whatever option you want there. I'm going to do 10 and 10. Now, 10 and 10 are already a pair. So once you get a pair, even though they're not primes, you could actually take it out. If you don't realize that or whatever, or just explain it, each 10 would break out into 2 and 5. So what's going to end up happening here is you have a pair of 2s, right? Then you have a pair of 5s. So you're going to take out a 2, you're going to take out a 5, and then this 3 is left over. 2 times 5 is going to multiply back to that 10. So you see, if you had the pair of 10s and you just realized right then that, oh, I have a pair, you could have taken that 10 out right away without breaking it down some more. Okay, so then the next few problems, same idea. The only difference is now we have a number in the front. We have this coefficient here. So the only thing is that's an added step at the end where you're going to multiply that coefficient to your simplified answer. So the 18, we're going to use our factor tree method. You could do 3 and 6 or 2 and 9. The 9 can continue on with factoring. So now I have a pair of 3s, so a 3 comes out. I have a 2 without a pair, so that's going to stay in. Now be careful. Don't think you're finished because you had that 2 from the beginning that has to get multiplied to that answer. So it's 6 times radical 2. Okay, number 5, 52. So I'm going to do 4 and 13. 4 further breaks down into 2 and 2, and those are my 3 primes. The pair of 2s, I can take a 2 out. The 13 does not have a pair, so it stays in. And then this 3 is going to have to get multiplied here to the front. So that's going to give me 6 times radical 13. And number 6, 605, I believe that is 5 and 121. And 121 breaks into 11 and 11. Now right there I have a pair of 11s, but they're prime anyway, so I can't do any more. So an 11 is going to come out. The 5 does not have a pair, so it stays in. And then this 4 is going to multiply to my 11 in the front. And then I have 44 times the radical 5. Okay, so 7, 8, and 9, going back to that product property of radicals from the first page of the notes. Anytime you have 2 separate radicals that are being multiplied, you can just multiply the 2 numbers. 5 times 10 is 50, but that answer goes in the radical symbol. Now, the only time you wouldn't want to do that is if one of these individual radicals happen to be a perfect square, then you might want to just simplify that. But since 5 and 10 are not perfect squares, I'm just going to multiply them to 50. And then I'm going to do my factor tree like we did on the other 6 problems. Now, at this point, if you want to do your factor tree, you could just do 5 and 10 and use the numbers that already split up into, or maybe you want to do a different grouping and you want to do 2 and 25, and then the 25 breaks into that pair of 5s. So then I'm going to take out my 5, and the 2 stays in, and that's my answer. Had you done 5 and 10, then the 10 would have broken down into a 5 and 2. You would have still had a pair of 5s and 1, 2. Okay, number 8, 3 times 12 is 36, and you may or may not realize that this is itself a perfect square. So if you notice that 36 is a perfect square, you can just then write the answer is 6. If you don't notice it, let's just say you're like kind of not really paying attention and you don't really notice that 36 is a perfect square, and you're like, oh, I'm going to break this into 9 and 4. Well, then now you have your 4, which is 2 and 2, and a 9, which is 3 and 3. So a pair of 3s, a pair of 2s, 2 times 3 is 6. You can still get the answer. I mean, obviously, you wouldn't want to have to do that work because it's not necessary, but it is a nice little built-in kind of backup plan if you do not notice that a number is a perfect square. And then 6 times 15 is 90. You could break it into 6 and 15, or if you rather do like 9 and 10 or something like that, that's fine. My 9 is going to go into 3 and 3. My 10 is going to go into 2 and 5. My 3 has a pair, so that comes out. My 2 and my 5 do not, so they get multiplied and they stay back in. Okay, so for 10, 11, and 12, we now have coefficients on each of those radicals. So just like we were doing before, I'm going to multiply the 12 and the 2, so that's going to give me 24 inside my radical, and the two numbers that are outside the radical will also get multiplied, and their answer will go outside the radical, so 6. Then you're going to continue doing what we just did. So I'm going to break up my 24. Maybe this time I'll do 2 and 12. My 2 is prime, but my 12 can then go to 2 and 6. And my 6 can go to 2 and 3. So first thing I'm going to do is I have a pair of 2's. So maybe I'm going to use this pair of 2's here. So that 2 comes out. This 2 and 3 do not have a pair, so that's going to get multiplied and stay in. But then that 6 has to multiply to that 2 that was out front, and my answer is 12 times the radical 6. Okay, number 11, 6 times 10, they're both inside the radical, so they get multiplied together and the answer goes inside the radical. On the outside, I have a 4, and this would basically be a 1. 4 times 1 is just 4. Now I want to break up my 60. You can do 6 and 10 or some other combination of numbers that multiply to get 60. So now I'm going to do 3 and 2 for the 6, 2 and 5 for the 10. So I see that I have a pair of 2's there. So I have a 2 coming out of the radical. The 3 and the 5 are going to get multiplied and they're put back into the radical. And then this 4 has to get multiplied to that number out front. So that'll be 8 radical 15. Okay, number 12, 3 times 21 is 63. And the two coefficients, the 5 times 2 is a 10 on the outside. Now my 63, I'm going to break up into 9 and 7, and my 9 can further break down into a pair of 3's. Pair of 3's tells me a 3 comes out, that 7 all by itself stays in, and then that 10 is going to get multiplied to the front, making it 30 radical 7. Okay, so now we're going to go into the fractional ones, which are basically dividing, right? So these are quotients inside a radical. Now, the first thing I would suggest that you always do is try to simplify it first before you do anything else. Sometimes you can, and that will make the rest of your problem work out a little bit easier because the numbers will be smaller and easier to work with. If they're not simple, if it's not something you can simplify or reduce, that's fine, but it's always worth it to check that first. Now, once you've checked that and you see, like in numbers 1, 2, and 3, none of these are something we can simplify, then you want to go ahead and break it up into a separate numerator and a separate denominator. So radical 7 on the top, radical 16 on the bottom. Once you do that, you're going to simplify them as two separate situations or separate problems or scenarios or pieces or whatever, and then see what you end up with. Now, 7 is a prime, so there's no simplifying I can do with that. It's just going to stay radical 7. But 16 is a perfect square, so it's just going to equal 4, and that would be my answer. Now, even though I have a 4 on the bottom, it's okay because it's not in a radical. Okay, number 2, I want to break this up into an 8 and a 9 separately. Now my 9 works out nicely into just a 3, right? Square root of 9 equals 3. But 8, I'm going to have to do my little factor tree for that one. And that way I can get my answer there, which is 2 radical 2. And then that's what's going to be in my numerator. Now just double check if you have a number that like this 2 that's not in the radical anymore and this 3 on the bottom that's not in a radical, those could be simplified or reduced if the numbers allow you to do so. Okay, and then number 3, we have the square root of 49 separated over the square root of 25, and these are both perfect squares, so you're going to get a nice answer of 7 over 5. Okay. All right, so now for 4 and 5, this is where that simplifying in the beginning comes in handy. So I don't have to do square root of 90 and simplify it and square root of 2 and rationalize my denominator, which would be a whole big thing. If you notice, 90 over 2 just simply reduces to 45. All you have to do now is your tree for that 45. So 9 and 5, 3 and 3, and then I'm going to have 3 radical 5. You could still get that answer doing it with a whole bunch more work, but why would you want to do that, right? Okay, so let's take a look at the next problem. Okay, so this one, 48 divided by 3, is going to be, I believe it's 16, good, which is a perfect square, so then that's just going to work out to be 4. Okay, and then number 6, 2 fractions, neither one of them can you reduce or simplify the way it is. So then we're going to multiply 2 times 8, which is 16. That's on the top. Then you multiply the two denominators and you would get 9. And the square root of 16 is 4, and the square root of 9 is 3. So that works out nicely to a fraction there. Okay. So now for 7, 8, and 9, we need to get rid of this denominator. We do not like having a radical in the denominator. It's definitely not something that we want to keep there. It's against our rules, so to speak. So this would not be considered fully simplified. Now, in order to get this radical to go away, we need the number inside to be a perfect square. So what number can I multiply 3 by so that I have a perfect square in there? Well, it's pretty simple. You multiply it by itself, because if you multiply any number by itself, what you get is going to be a perfect square. So any number that's on the bottom inside a radical, you're going to multiply it by itself, because 3 times 3 would be 9. And then, of course, that's a perfect square, which means I can solve my radical, square root of 9, which equals just 3. So essentially, anytime you multiply a radical by itself, the number will come out of the radical. Now, with this kind of situation, anything you do to the bottom of the fraction, you also have to do to the top. So I'm also going to multiply my numerator by radical 3, which gives me 2 radical 3. And that just carries over. Now, if there was some simplifying I could do or something, like I'd have to do my factor tree or something like that, I would have to do it. But 3 is a prime, so I can't take out any more there. And then the 2 on the top and the 3 on the bottom, there's no simplifying or reducing, so that's my answer. Now, when I go to number 8, this time, I'm going to multiply the bottom and the top by radical 5. So then on the top, I have 6 radical 5. On the bottom, I have square root of 25, which really just equals 5. So you don't even need to write that middle step necessarily unless it helps you. And then the 6 times radical 5 over 5. Now 6 and 5 do not reduce or simplify. The 5 inside the radical on the top is as simplified as it can be. So there's nothing else for us to do there. Okay, and then number 9. Okay, same concept. We're going to multiply this radical by itself. When we do that, we end up with 5 radical 10 in the numerator, and then the bottom is square root of 100, which is just going to be 10. Now, this is one of those situations where the 5 and the 10 can then be simplified, right? Because that reduces to 1/2. So your final answer here would be the radical 10 over 2. You don't need to put the 1 in front of the radical. It's just like when you have an x or something, you don't have to put the 1 in front. Okay, and our last 3 questions on simplifying radicals. Number 10, okay, fraction. First thing I'm checking is, can I reduce it as it is? I cannot, so then I'm going to separate it into a numerator and a denominator. At this point, neither one is a perfect square. I can't simplify either one of them, separately because they're both primes. So I'm going to rationalize my denominator here by multiplying the top and the bottom by radical 2. Now, when I do that, I end up with radical 14 on the top and just regular 2 on the bottom. The 14 does not break down because it only goes into 2 and 7. There's no pairs there to take out. So that's as far as we can go. All right, number 11, this does not simplify or reduce the way it is, so I have to separate it. The 49 will work out to be 7. However, I still have a radical in my denominator. So now I'm going to rationalize by multiplying the top and the bottom by radical 5. And I get 7 radical 5 on the top and just regular old 5 on the bottom. 7 over 5 does not reduce, so that's as far as we can go. And then number 12, these do not simplify individually, so I'm going to multiply across my 2 numerators. I have the radical 35. My 2 denominators, I get radical or square root of 36. On the bottom, I know that's a perfect square, so it's going to equal 6. And then my 35, I might need to do my factor tree, right? Except I notice it just goes to 5 and 7. There's no pairs or anything, so it's just going to stay square root of 35 over 6, or radical 35 over 6. Okay, so that's the first half of our lesson here. And so the second half is we're going to now apply this to help us solve those quadratic equations like we were doing in earlier sections with the other methods. Remember, all positive numbers have 2 square roots, a positive and a negative, and so that's important. So if you have a number in your square root that is a positive number or greater than 0, you're going to have a positive and a negative root for that number. So you're going to have 2 solutions. However, if in the event that you would get a 0 for your number and you're trying to take the square root of a 0, there's only one answer, x equals 0. So in that situation, you would only have one solution or one root or one x-intercept. If you have a number that's a negative, you can't take the square root of a negative number, so you're going to get no real solution. Now, if you had a parabola for any of these 2 solutions, your parabola would cross through in 2 spots. For one solution, your parabola would hit the x-axis in one spot. For no solution, it's because your parabola will not cross the x-axis. So that's where these kind of correlate to the graphing that we were doing earlier. Okay, so solving each quadratic equation by using the method of square rooting. So this method can really only be used when you have something squared, like an x squared, and you have a constant, but no other variables. So if you have an x squared and an x and a constant, like we had when we were factoring or when we were graphing, this method, you can't use it. You'd have to use a different option, and we'll get to the rest of those later in this chapter. But this method is probably one of the easier methods, but obviously it has limitations. You cannot use it when you have an x squared and an x. So if you only have an x squared, you want to get it by itself, just like you would normally if you were solving a linear equation. So number 1, we already have the x squared by itself. Now, the inverse operation for squaring would be square rooting. So if I want to get rid of the little exponent on my x, I'm going to square root it. Or whatever I do to one side, I do to the other. Now, the one kicker here is, and this is what everyone always kind of messes up on, is that they'll get 4, but they forget that it's positive 4 or negative 4. I don't know why my pen's kind of bugging there. Okay, so let's take a look at the next problem. All right, so now this one, again, we need to get this x squared by itself. So I'm going to divide both sides by the 2. So that x squared is by itself. And then over here at 36. All right, now I can get rid of my square root by my square by square rooting it. And let me see if I can switch to a different pen that doesn't make these weird. No, it's still doing it. And then my answer here would be positive or negative 6 because the square root of 36 equals 6, but I need both the positive and the negative answer. And these are the two locations where that parabola would cross through the x-axis. Okay, now number 3, I have an x squared. It's already by itself, so I'm going to go ahead and square root both sides, leaving me with x. And on this side, I would have positive or negative square root of 12. Now, this is where you can do your little factor tree. So 3 and 4, the 4 will break down into 2 and 2. And then I'm going to have 2 radical 3. But again, plus and minus. So x is going to have 2 solutions, positive 2 radical 3 and negative 2 radical 3. Okay, so for the next few problems here, we are going to get those x squareds by themselves, noticing throughout those problems there's no other variables here. There's no x's or y squares or anything else. So I know that I could do this. Okay, so -1, so I'm just going to subtract that from each side. Now I want to divide both sides by the 2 to get my x squared by itself. And then we're going to square root to get rid of that x squared. So it's just x equals positive or negative square root of 8. Now again, you have to make sure that radical answer is simplified. So for my 8, 2 and 4, the 4 breaks down into 2 and 2, which is a pair. So x equals positive or negative 2 radical 2. And that's my answer for that one. Okay, for number 5, we're going to subtract 5. So I'm left with 2x squared equals 36, I believe. Divide by 2. And then we're going to square root that. So x equals positive or negative square root of 18. But that's something I can break down. So 2 and 9, 3 and 3. So x equals positive or negative 3 radical 2. So there we go. Okay, let's take a look at number 6. So number 6, I'm going to add my 12. So I have negative x squared equals, and I believe this is going to be negative 75. Now, I can't have a negative on my x squared, so I'm going to divide that out, which is going to switch the sign of my 75. Now, I want to square root both sides so I can get my x. And I have positive or negative square root of 75. Make sure you use your little factoring to get that simplified. So 3 and 25. 25 breaks down into 5 and 5. So x equals positive or negative 5 radical 3. Okay. All right, so now these problems are a little different because we see that there are some parentheses involved, right? So we only see like an x here, but then we also see this exponent. So it actually, they're in vertex form, if you remember that vertex form that we did from graphing. Now, when we're doing something in this vertex type of form, we can still use this method of square rooting because there's only the one variable. We just have that one x inside the parentheses. Now, one thing that sometimes people go to do is they would write x plus 5 twice and try to FOIL it. But you can do it that way, but then you won't be able to use this method anymore because once you do that, you're going to have an x squared and also some x. And then you can no longer use this method. But in order for me to just get rid of this square here, I just have to square root both sides. So now my x plus 5 comes out the parentheses, and my square root of 11 is over here. And remember, that's really a plus minus square root of 11. So now I'm going to subtract my 5 to the other side. And I have x equals -5. Oops, sorry, it's really hard to write when it keeps jumping like this. Plus or minus radical 11. That looks, I wish it would not do that. It's very tricky here because it's not showing up right. I don't know, I must have hit some button that's making it go wacky. X equals -5 plus or minus radical 11. Hopefully that looks a little better. Okay, not sure what's going on there. Okay, this one here, before we do anything with that, we got to get rid of the 2. So x minus 3 squared will equal 4. Square root to get rid of that little exponent, x minus 3 equals positive or negative. Now this one's nice because the square root of 4 actually equals 2. And I don't know what's going on here. Okay. And then we would just add 3. So x equals, and you're going to do 3 plus or minus 2. Now you can actually calculate 3 plus or minus 2 because 3 plus 2 equals 5. So that's one solution. And 3 minus 2 is 1. Oops. And so that would be our other solution. Let's try that again. X equals 1. Okay, so we have 1 and 5. All right, and then our last problem here, we would have to divide by this -3. That would give us x plus 2 squared equals 6. The square root both sides, so my x plus 2 is now by itself, and I have positive or negative radical 6. Subtract the 2 to both sides. When you do that, that number has to go in front of the radical. So it'd be -2 plus or minus radical 6. Now you could actually put that on the calculator and get 2 decimal answers, but I'm not concerned about those right now. If you were going to put them on the calculator, like -2 plus or minus radical 6, you would just type it in like that and get 2 separate answers. So you would type them in 2 separate times, once with the plus and once with the minus. Okay, so I'm going to stop there just because my computer's kind of bugging out. If you have any questions on any of this, please contact me and let me know. Thanks.